Okay, here's an advanced trick for dealing with inverters and such. And actually, it's copies of everything. Bus notation. That is the name for today. Bus notation. You see, we have three inverters. They are identical. They're just three copies. They're also connected together in series or in cascade. And we named them A0, A1, A2, A3, and so on. And that's really nice. But what if we had 100? It would get really tedious. We'd get probably a carpal tunnel in your mouse hand, and that would be unfortunate because there's features of these CAD tools that we are going to use right now. Here it is. To do this, we're going to make a new new schematic. So we're going to say right-click on white inverters, create new cell, white inverters schematic. We say test INV bus, just for a nice name. Alright, so we have INV bus opened up. Turn the grid on, Control G because it looks nice. Components, we're going to add our inverter cell. Right now we're just going to add one. Control I. Alright, so we're editing the properties of this node, which is a cell instance. Its name is INV1 at 0. That's just the default name. Its type is INV1. It's the icon view. It does not have to be named INV1 at 0. We can name it whatever we want. Here's what we're going to do. We want to have 10 copies of this. Alright, so we're going to have 10 copies of this INV1. How about let's keep the INV1 because we like it. Now let's just call it INV. INV. Here comes the bus notation. Square brackets. Numbers in the square brackets are broken out. It's like bus notation or bit notation and such in VHDL and Verilog. Very much the same. I want to name these in order. I want to have 10 of them. I want the first one to be 0. It's all my choice. But you're listening and it's not your choice. So 0, 9. That is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10 total. Just as it is in Verilog or VHDL, those sorts of things. Say OK. Do you see what happened? Actually, one side note is this INV1 that's at the top. It used to be in the middle. I moved it up because now we can see the name. Zoom in here. So INV1 is the type, it's the cell name, but INV bracket 0, 9 close bracket, that is the instance names. MOSFET number 1, MOSFET number 2. It is a MOSFET, but whatever. So what we have here is we're looking at 10 copies of this, but just with one symbol. This is insanely powerful, by the way. However, we want to wire inverter 0 to inverter 1 to inverter 2 to inverter 3. We want to make a chain that just goes all the way across. Well, how do we do that? If we can cleverly name the inputs and the outputs, we can name them in bus notation. This one requires that you do be a little bit careful, but it's insanely powerful. Over here, use arc wire. That's just for single nets, single circuit nodes, nets. We want to use a bus, heavy green wire. So we're going to attach it. We're going to select this, attach a bus to the left side, just drag it out for a little bit, which it did not do. So here, we want this one. There we go. See the little red plus there? There's a little plus over there. Make sure the port plus on the left side is connected. Drag it out. Okay. Select again. Port over here. So now we have a bus hanging on either side, the input and the output. Let's name this bus. Double click on it. Its name is net 0. However, we're going to call this a bus that has multiple things in it. We're going to call this A, open bracket, 0 through 9. Actually, I'm going to say 0 through 8 and see what happens. Hit F5. We always have to do that to do our design rule check. It found 2 errors. What are the errors? 1 error, arc bus A0 through 8, which is 9 wide, connects to export in of node INV1, whatever, is 1 wide. We can't do that. We have 9 inverters, or 10 inverters, but only 9 wires. There's not a way to actually hook that up. So we made a mistake. Alright, exit out of error mode. Change this name to 0 to 9. It connects them in this order. F5 again. 1 error. What's our error? The arc dangles. Okay. We'll forget that for now. You know, I don't like how it buried that, so we'll redraw this bus. Here, here. Drag it out. Name A0 through 9. Okay. We zoom in here, we see it. Can we get this name like out of here? No, whatever. That's okay. This one. Alright, first of all, bus A0 through 9 connects to inverter 0 through 9 at the input. So A0 connects to inverter 0. A1 connects to inverter 1. We could name these backwards, which is really fun. It blows your head, but it's great. A9 connects to inverter 9. What we want is we want inverter 0, the output of inverter 0, to connect to A1. So we name this bus in a super tricky fashion. We can't say A0 to 9. It is true, it's 10, but now we connected for every inverter, we connected to the input to the output, and they're not in series. Hope that was explained okay. We still need 10 nodes, but we want the output of inverter 0, which is the first one, to go to node or net name A1. So we're going to say A1 through 10. That's exactly what we want. Okay, so there's 10 total. There we go. Let's see if we have any errors. F5, schematic checking, 0 errors, 0 warnings. That's what we want. We have now chained 10 inverters in series. Oh yeah. At the first part of this chain, we have node A0, that's the input. The output is node A10. Those are the nets on the outer ends of this. We can connect in the middle, but we really don't need or want to in this case. What we are going to do is simulate this. We want a SPICE pulse source. Slap it down here. Do you notice how we changed the SPICE thing and the names are out here? That's much better. We want a wire. We're going to take a wire. This is just one. Go from here to the bus. And if we say F5, we get an error. We get an error. What's the error? What's the error? Wire arcs do not connect to bus through a bus pin. What if I just name it? A0. A0. Try that. F5. No errors! What happened is, just like in schematics, if we name a node or a net, they connect. They don't have to be drawn together. There's also a symbol that's like a connect a wire to a bus. I'd have to look at the manual a little more to see how to read that, but this works just as well. Alright, minus needs to go to ground, of course. Add a wire. Connect that up. Makes the noise. Okay, our pulse voltage still is 3 volts. We could have changed the default, but we didn't, I guess. Rise time, 10 pico. Fall time. Actually, let's do that. Let's erase this thing. Erase that. Erase that. Go back to our Explorer. Open up SPICE parts. Find our pulse in here. Open up the pulse. We're going to use 5 volts all the time. Let's set the defaults to this. So 10 pico, Fall time of 10 pico. Pulse width of 3 nano. I don't know. Let's back it down to 2 nano in a period of 4 nano. DC voltage we're not using in this case. Okay, save. That's great. Go back to our schematic. Components, SPICE, add our pulse, and if you see, the defaults show up. So we don't have to change them unless we're doing something other than the default. Very convenient. It's totally roll your own in chip design and circuit design. Still need to name this node again. Double click, name it A0, A bracket 0 to get the bus notation. And we'll move it over because it looks prettier. We want to run a simulation, so we need the miscellaneous SPICE code. So we'll do SPICE code, double click, Control I, multi-line text, dot include c5.txt. If you make it a short name, you don't have to type as much. Okay, and we'll just do our simulation here also. .tran, what worked good for us? 10 pico, and run this for, let's see, 2 cycles, 4, 8, 10 nano. Okay. Can we simulate? Let's find out. Running SPICE command. Yep. It does it. Hey, this is wonderful. Now, do you see what happened? This is the best way to see how your bus notation works. Is dump a netlist. We have one sub-circuit. VDD and ground are here. Our SPICE codes is just dumped here. Include the models. That's why LT SPICE didn't complain. Include power and ground. And make sure that we connect GND to node 0. Node 0 is the special one. It's the actual 0, ground, whatever in SPICE. LT SPICE sometimes connects GND and 0, but let's do it explicitly. Explicit is always better. Transient simulation, and so on. So here we go. Here's our pulse. Pulse came in as we wanted. And now we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 inverters. They're all instances of INV1. Node A0 is connected to the pulse. A1 is the output of the first inverter, and A1 is connected to the input of the second inverter. This is where bus notation shines. Shines. If we need a register that's 64 bits wide, that's like 64 D flip-flops, we can do that with one symbol on the schematic and name it appropriately. Buses, man. This is digital stuff. We're going to have tons and tons of wires. Bus notation is in your advantage. Read up on the electric manual for bus notation. And you can also look up bus notation in Cadence, because the syntax is it's really the same. I guess in Verilog too. Okay, so that's that. We didn't really plot anything. Pick visible traces and 0, 1. Actually, let's start at A1 and look what happens at A9. And there we go. The delay gets larger. A1, 7, 5, 3. Every other one, we should see rise, 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 rise. No inversions. And you can see we have a delay. This is 2 delays through here. 2 delays, 2 delays, 2 delays, 2 delays. Or a rising delay and a falling delay. And so on. There we go. That's all we need. Calculate our delays. Move on. In SPICE, we can use the dot measure command here. Write out that command. If we go to the LT SPICE manual, PDF version is much better. I'll have that on Blackboard. LT SPICE dot commands. Just look up dot measure. Here's the include that we used. can use library also. It works fine. Dot measure. Dot measure has lots of terms that come with it. There's the syntax, lots of ways to use dot measure, and what it does is it measures some quantity that you want, crossings, times. You can do math, you can subtract times, like the crossing of this waveform and the crossing of that waveform, find the times for each, subtract them. That is your delay by definition. A couple dot measure lines, and then it will output to the log. If you look at the simulate tools, view the SPICE error log, Control L. This is the output that usually you don't look at, but what will happen is when you use dot measure, it writes to this log. It'll write a line that says your measure number, measure name Billy Bob had a certain name in there, and you just look at the delay time. You don't even need to look at the waveforms once you know your circuit is working correctly. That is awesome. As you know, like LT Spice, doing the cursors, it can work if you're just making one measurement, but not for lots of them. Not saving that, so on. So please save your work. If you try to exit without saving, LT or Electric will ask you, but there we go. There's the hard way. There's the easy way. I know which one I prefer. It's up to you to decide otherwise.